All right, so in this example, or in this video, I'm going to work an example involving multiple reactions in a batch reactor, and specifically this batch reactor is going to be run non-isothermally. But it's going to be, the reaction is carried out in the liquid phase, so the volume is constant. Okay, so the problem statement reads, the following reactions are taking place in liquid phase in a 2,000 liter batch reactor. We're given a set of 3 complex reactions. For each of those reactions, we're given a heat of reaction. The heat of reaction is in terms of a particular species. And we're also given a rate law in terms of a particular species. And notice that for all of those reactions, the heat of reaction is given in terms of a different species than the rate law. So we're going to have to do some converting of units. The problem statement reads, the initial temperature is 450 Kelvin and the initial concentrations of A, B, and C are 1.0, 0.5, and 0.2 molar respectively. The coolant temperature, so that's in the heat exchanger, so this is a batch reactor with a heat exchanger. The coolant temperature is constant at 400 Kelvin, so this means that for the coolant temperature to be constant, that means that the flow rate of coolant is moving through the heat exchanger pretty quickly. And we're given a value also for the heat transfer coefficient of 0.1 kilocalorie per second per Kelvin. Given the following information, plot the concentrations of the different species, so the concentrations of A, B, C, D, and E, and also the temperature for time up to 1 hour. And then we're given data here about the values of the rate constants as well as the heat capacities of the different species. So I'm going to start the way we always start, and that's to write the mole balances for the different species. And I'm going to take advantage of the fact that this is a constant volume batch reactor. The general expression for the batch reactor mole balance is to write in terms of number of moles. I'm going to write in terms of concentration because the volume is constant, and I can do that. So batch reactor mole balances, I'm going to write dCA dt, and that's going to be the net rate of generation of species A. dCB dt equals RB, dCC dt equals RC, dCD dt equals RD, and dCE dt equals RE. So those are the rate of change in the concentration is going to be equal to the rates of generation of each species. And notice that our units are consistent here. On the left-hand side, we have moles per volume per time, and on the right-hand side, we have moles per volume per time. All right, so now I need to write my net rates of generation for each species. So I'm going to go back to my problem statement here and basically look and see which species are involved in each reaction. So species A is involved in reactions 1 and 2. Species B is involved in 1 and 3. Species C is involved in all 3 reactions. And then species D is involved in reaction 2, and species E is involved in reaction 3. So my net rates of generation are going to reflect that. So I have net rate of generation of A equals R1A plus R2A. Net rate of generation of B is going to be R1B plus R3B. Net rate of generation of C is going to be R1C plus R2C plus R3C. Net rate of generation of D is just going to be R2D, and then net rate of generation of E is just going to be R3E. Okay, so now these, what I've written down here, are my net rates in terms of my relative rates. So next I'm going to write my relative rates. I'm going to do this for each species in each reaction. So I'm already given information on the net rate, or the relative rates of A for reaction 1, of A for reaction 2, and of C for reaction 3. So I already have that information. I'm going to write the relative rates for all the other species in each reaction in terms of those, in terms of the relative rates I already have. And again, I'm going to do that using the relative rates equation. So let me do one example. Let's take species B in reaction 1. So if I want to write this in terms of species A, because I have that information, I'm going to say negative R1A divided by negative 1. So the stoichiometric coefficient on A is 1, and A is a reactant, so I'm going to make that negative, is going to be equal to the relative rate in here. I actually made an error here. So the relative rate of generation of A in reaction 1 divided by its stoichiometric coefficient. I'm now going to make that equal to 1B over its stoichiometric coefficient, which is 2. B is also a reactant, so it's also going to be negative, and because of that, I'm going to solve for R1B is going to be equal to 2R1A. So I can go down and write that here. R1B is equal to 2R1A. And now I can go through and do that for the remaining species. R1C is equal to negative R1A. R2C is equal to 3/2 R2A. R2D is equal to negative 2 R2A. R3B is equal to 1/3 R3C, and R3E is equal to negative R3C. So that gives me my relative rates, which I can now put into my net rate expressions. I've already got expressions for my rate laws. Those are given in the problem statement. What else do I need here? That might be, I'm going to need an energy balance. I'm going to get that in just 1 second. Okay, so this is a non-isothermal reaction. Therefore, I need to write an energy balance. I'm going to write down the general energy balance equation for a batch reactor. So that's going to be dt is equal to, in my numerator, I'm going to have my heats of generation and removal, and in the denominator, I'm going to have my sensible heat changes. So the heat generated is due to the reaction. That's going to be equal to the volume times the heat of reaction times the rate of each reaction, and that is going to be, I'm going to need to sum those for all 3 reactions. So I'm given heats of reaction in terms of species B for reaction 1, species C for reaction 2, and species B for reaction 3. So I need to say my heat of reaction for reaction 1, and this is in terms of B, so I'm going to put a B here to kind of denote that. And then, because I'm writing the heat of reaction in terms of species B, I also want to write the relative rate of species B for reaction 1, so that's going to be R1B. And here I have a choice on how to make a sign. I'm either going to make both of these be positive or both of them be negative. And if I think about what that's going to do, if I go back to reaction 1, the heat of reaction is negative. It's an exothermic reaction. It's going to give off heat. It's going to increase the temperature. So then this quantity right here is going to be negative. Species B is a reactant in that reaction. So this quantity here, the rate of generation of species B in reaction 1, that's going to be negative. So this is going to be a negative times a negative, which is going to be a positive. So that means that this reaction is going to increase the temperature. So that's exactly what we want. That's consistent with chemistry. Okay, so now let's do this for our other reactions. The heat of reaction 2 is in terms of species C. So I'm going to write the relative rate of species C in reaction 2. And then I'm going to do reaction 3 is in terms of species B. So I'll take the relative rate of species B in reaction 3. Okay, so that gives me my heat generated term. That's all multiplied, going to be multiplied by the volume. Notice that the heat generated is larger if the volume is larger. Okay, in this reaction I have a heat exchanger, so my heat removal term is going to be the heat exchanger term. I'm going to have T minus TA here. If I look at the argument here, T minus TA, if the reactor temperature is greater than the ambient temperature, I have a leading negative sign out here, so that's actually going to decrease the temperature, so the coolant is doing what it's supposed to. If the reactant temperature is hotter, it's going to transfer heat to the heat transfer coolant. That's the way heat transfer works, and so when I check this, I'm going to make sure that accounts for the temperature properly, and it does. Okay, so now that's all just my numerator of my energy balance. Okay, so in the denominator, I'm going to have my sensible heat changes, and that's basically going to be the number of moles of each species times the heat capacity. So that's going to be NA times CPA plus NB times CPB plus NC times CPC plus ND times CPD plus NE times CPE. And so let me kind of zoom out here to kind of show this whole equation. So this is my energy balance expression. All right, now looking at this, there's a couple of things. One, I have values of N here, number of moles, but I've written everything in terms of concentration. That means I'm going to need to set up my problem with conversion factors. So we'll say equations for number of moles of each species. I can get that by multiplying the concentration of each species by the volume. So this is just a conversion factor. Na is going to be equal to Ca times V. V is this 2,000 liters. And B equals Cb times V, and C equals Cc times V, and D equals Cd times V, and then E is equal to Ce times V. So that gives me my number of moles. I'm missing something else here. And that is the fact that this is a non-isothermal reaction. My rate constants are not constant. They're going to vary with the temperature. So I would need to write down the Arrhenius equation. And I never am sure about how to spell this. I would need to write down the Arrhenius equation for each species, or for each rate constant. So for example, K1A would be equal to K1A 0 times the exponential of the activation energy of reaction 1 divided by the gas constant divided by 1 over T naught minus 1 over T. And same for the rest of them. The problem here is I'm not given values for the activation energy in the problem statement. So I go back up here, I'm not given any of this information. So we're gonna have to do something about that. And I'll show you what I'm gonna do. I'll show you what I'm gonna do in just a second. All right, so I think that is all I need then to write down, and I can now take this and put this into a math solver. Okay, so here I have put the multiple reactions in a non-isothermal batch reactor. I've put that information into Python. Again, probably the number of explicit equations I'm going to have to need to use is going to be larger than 10, which makes it, which means it's too large to use in the Polymath Plus free online solver. So I'm going to use Python. All right, so first cell here, I'm basically loading in the modules I need, and some I don't need. I basically just carry these with me. Okay, so here is my constant data. So I'm using, this is my volume here. I'm using a 2000, what is it? 2,000 liter batch reactor. So that's 2,000 liters. I was supposed to integrate for an hour. I'm going to integrate for 1,000 seconds, and then we can integrate for an hour after that. So this is my integration space. Here are all of my heats of reactions. The species, which they are in terms of, is indicated here, and these are going to be in kilocalories per mole. We ended the development of the equation saying what we really need are activation energies, but we don't have those. So let's take, the rates are going to be fastest when the activation energy is equal to 0. So the minimum value for activation energy is 0. So let's take a look at that case as a limiting case and see what happens, and then make a choice about what to do after that. Okay, so now I have here my gas constant. I want to use units of kilocalories per mole Kelvin to be consistent with the other units in the problem. This is my initial temperature of the batch initially. I have here some, if I wanted to add an inert, I kind of threw this in as an example. You don't need to have this in your solution, but this would be the number of moles of inert and then turning that into the concentration by dividing by the volume. We don't have any inert in our system, which is why this is 0. Here are all of my initial concentrations. This is the temperature of the cooling fluid and the heat transfer coefficient. And that is going to be in units of kilocalories per second per Kelvin. These are my rate constants. These are have units of, well, they're going to use molar for the concentration units. The units on each one is going to be different depending on the reaction order, but the time units here are going to be seconds, which is consistent with the heat transfer coefficient, and the temperature units are going to be in Kelvin. And then I have all of my heat capacities as well. And those are going to be, I have those entered in units of kilocalories per mole Kelvin to be consistent with the other ones. Here you'll see I've added in a heat capacity for an inert species. Again, we're not using an inert in this problem, but the heat capacity was based off of a common type of inert species, which might be argon or molecular nitrogen. All right, so let's run that cell. Here I've defined the function that is going to solve this batch reactor. I've called it batch. Again, we can solve it, we can call it whatever we want, and I've said it's going to be in terms of z and t, and again, we can make those whatever we want. This is just kind of what I use. Here we're going to have six dependent variables, the concentrations of our different species A, B, C, D, and E, but then also we're going to have the temperature because this is a non-isothermal batch reactor. I end up needing expressions for the number of moles, so I'm going to define those. This is a non-isothermal reaction, so I should have my Arrhenius equation that calculates my rate constant as a function of temperature. Again, I don't have values for these numbers, so those numbers I'm setting right now is equal to 0. So what that does is the rate constants are constant. They stay the same since they have no dependence on temperature when I set the activation energy equal to 0. Here's my rate laws that I've copied in from the problem statement. Again, I use this double asterisk in place of a caret symbol in Python. Here's all the relative rates that we wrote down. Here's our net rates of generation that we wrote down. Here's all of our mole balances that we wrote down. This is our energy balance, and then this, basically I coupled them together here and tell the solver to return back to me the concentrations. Here's my list of initial conditions. I've defined all of these above, and here's what I'm going to use to solve. When I solve the equation, I want to report back all the concentrations and the temperature because those are what I want to plot. And so then I can run this cell, and as you can see, I've already done that before. And I'm going to plot out my concentrations in one graph and my temperature in another graph. So here's what I get for the first 1,000 seconds. I have A kind of reacting away slowly, B kind of reacting away slowly. I have C, I start out with initial concentration of C, which kind of goes up gradually and then starts to react away. So what's going on there is the first reaction turns on, A and B react to form C, but then C starts reacting with A to form D, and as that's happening, the concentration of D is increasing. B and C also react to form E, so you see that increasing. So the rate of growth of C is pretty short-lived because C starts reacting away. Another thing we see here is that my temperature, the temperature initially starts out constant. So the first couple of seconds, I have the temperature remaining constant, and then it falls. So several things about this. If the temperature is decreasing the whole time, that means that the rate constant would be decreasing. So right now I don't have any temperature dependence in my rate constant. But if I did, then they would decrease, which means that the reactions would proceed more slowly. And this would mean that what I have here is that the heat removal is more effective than the heat generating. So there's more heat removal than there is heat generated because the temperature goes down. If my rate constants were getting smaller due to my temperature getting lower, then my heat of generation, or my heat generated term, would be even smaller. So my heat removal term would be even larger. The difference between heat removal and heat generated would be even bigger. Because of this, what I'm getting here is actually a limiting case, and an actual case would actually have the temperature going down faster, would have those rates going slower. So that's a good thing. That tells me that my model is okay. So it's okay to model here the rate constants as constant because they're going to give me kind of a maximum heat generated picture. If I was modeling, if that was not the case and the temperature is going up and those rate constants were going up, this would not be a good model because the heat generated would be getting larger. And what I don't want to do is not account for the scenario where the heat generated term overcomes the heat removal term, because then I have the possibility of reaction runaway. So let's do a couple things here. Let's take a smaller T final. If we do this, then we see that we are pretty constant up here. So we start out in the temperature being, the temperature starts out being kind of constant before it drops off. So at the beginning of the reaction, the heat generated and heat removal are balanced, and then as the reaction proceeds and the concentrations start dropping, the heat removal term overcomes that of the heat generated term. So this is a pretty effective heat exchanger for the reaction that's being carried out. Now we were supposed to carry this out for an hour. So if we do that, we can see we're basically achieving the ambient temperature, the batch temperature, the system temperature is becoming equal to that of the cooling fluid temperature over the course of the reaction. We can also see here, what if we added in activation energies for the different species? How would that happen? What we see is the temperature comes even the, or it equates itself, or it approaches the cooling fluid temperature even sooner. This is because the reactions are going to run even slower as the temperature decreases. We see we get less conversion of species A. We get less formation of species D in this case.